This is quiz 21, and we have several problems having to do with differentials and linearizations. So the first problem has us find the linearization of the sine function at pi over 6. So our function is f of x equals sine of x, and at a equal to pi over 6. So we want the linearization, which is really the equation of the tangent line, only thought of as a function of x instead of just an equation. So in order to get the equation first, then we need the slope and we need a point. Well, if the point is pi over 6, we probably should get the y value. So what is f of pi over 6, just so that we get that y value out of the way? That would be the sine of pi over 6. And the sine of pi over 6, if we think of the unit circle, let's do that over here, out of the way a little bit. So on the unit circle, sine of pi over 6, the angle pi over 6 is 1/6 of the way to pi. So that would be a 30-degree angle. And the sine would be that segment, which is the shorter of the two sides. So that's going to be 1/2. Okay, so the point that we're talking about on the sine curve is x equals pi over 6, y equals 1/2. And we want the linearization of the sine function at that point. Okay, so we need the slope to get the equation of the line. So the slope, of course, is the derivative, and the derivative at any point would be the cosine of x, because the derivative of sine is cosine. But we're not interested in the derivative at any point. We're interested in the derivative at the point pi over 6. So we put pi over 6 in here, and we say that's going to be what? Well, cosine of pi over 6. And go back to the unit circle, the cosine of pi over 6 would be that horizontal segment, which is the longer of the two sides of a 30-60 triangle. So that's going to give us square root of 3 over 2. So now we're ready to write the equation. Y minus the y value, which we computed as 1/2, equals the slope, which is square root of 3 over 2, times x minus the x value, which is pi over 6. So if we write this in the y equals form, y equals 1/2 plus square root of 3 over 2 times x minus pi over 6. That's our y equals, and then that is our linearization. Now if you look carefully at this, you see nothing more than a line over on this side, because this is x to the first power. It's going to have a coefficient of square root of 3 over 2, and then all the rest of that stuff is constants. So it is a line. And if you were to graph this, which I can't really do right here easily, but if you were to graph the sine function, the sine function looks like this, and this point would be pi over 2, and pi over 6, this is pi here, so if you think of 1/6, this is 3/6, so 1/6 of the way would be about here. So at this point we are at y equal to 1/2, and the tangent line would be this line right here, and the slope of that line we already know is going to be square root of 3 over 2, and this formula would tell us the y value of any point on this line. So for example, if we plugged in pi over 2, which would not be a real smart thing to do, but it would give us the y value, and it'd be up here somewhere. Pi over 2 minus pi over 6 times square root of 3 over 2 plus 1/2. But this is the linearization. And the value of this linearization is that it gives us a good approximation for the sine as long as we're in this little window right here. Because if I don't have Maple on this computer yet, this particular new toy that I have, but I will soon. And if I did, I'd flip to it right now and show you that the sine locally looks just like that line. If you just put 1/2 plus square root of 3 over 2 times x minus pi over 6 into Maple and graph it, you would see that the line and the sine curve are almost the same as long as you stay reasonably close to pi over 6. And so this gives you a way of approximating the sine as long as you stay close to pi over 6. And this is an important principle. We're going to make use of a lot of this in future calculus courses, and you will make use of this in all kinds of ways in science. All right, well anyway, that's the answer to number 1. Okay, number 2 is considerably easier than this. All we had to do in number 2 is find a differential. So the differential for y equals e to the tangent pi t. So this is actually quite simple. All you got to do is take the differential of both sides. The differential of y is dy. The differential of this is just like the derivative of this. So the derivative of e to any power is e to that power again. But as usual, the chain rule has something to say. This exponent is not the independent variable, so you're going to multiply by the derivative of what's up there. The derivative of tangent of anything is secant squared of whatever. But that's not all, because this is not the independent variable. It's not t. So you got to multiply by the derivative or the differential of this. So that's just going to be pi. And then at the end you stick on d, whatever the variable is that you were differentiating with respect to. At this point it was t. So you have dt. And now you've calculated the differential of y. It's this times pi times dt. And that's it. It's really all there is to it. Notice that if you divided both sides by dt, you would have the derivative of y with respect to t. And this is correct. E to the tangent pi t back at you times secant squared pi t times pi. And that is dy dt. So you could think of calculating the differential by calculating dy dt. Just don't think about anything else. Find dy dt. And then in the end, you're going to have e to the tangent pi t times secant squared, blah, 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 pi. And then take the dt and throw it to the other side, and you got the right answer for the differential. That's really all there is to it. We're not going to do too much with that. You saw some practical applications. We'll see a little bit of it in problem 3, but we'll do a lot with it. You'll do a lot with it in calculus 2 when you get to changes of variables, where you have to maintain the relationship between the differential of one variable and the differential of another when you make a change of variables. Okay, number 3, we're supposed to compute delta y and dy for the function y equals square root of x, where x equals 1, at the point where x equals 1, with dx and delta x both equal to 1. And we want to draw a picture that shows everything. Okay, well, that's not too hard. You should know what the square root looks. Whoops, this is very bad. Let's try that again. You should know what the square root looks like. The square root is this sideways parabola. And it's only the top half. Okay, so when x equals 1, we're about there. So this, of course, is the point 1, 1. This is the graph of the square root of x. Now, when we talk about delta x being 1, then the change in x is going to be 1. So we should go from 1 to, say, 2. Or I suppose I didn't really make it clear whether it's going to be delta x this way or delta x this way. So you could do it either way. You should get credit either way. But let's go this way for 0. So if you take delta x to be 1 this way, then the delta y is the change in y. So delta y would be the difference in the y values, and that's just 1 minus 0, which is 1. And dy, by definition of dy, is the derivative, f prime of x, times dx. So we have to take the derivative of this guy, f prime, which would be y prime. So that's going to be, of course, 1 half x to the minus a half. And that derivative at this point will give us the slope of the tangent line right there. So the slope of that tangent line is going to be y prime at 1. So you plug in 1 for x, and that just gives you 1 half. Okay, so going back to here, that says dy is 1 half times dx, but dx and dy are the same, so that's 1, so this is 1 half. So dy is 1 half. So on your picture, dy, let's see, I need a better picture than this. This is pretty ugly. We should do it in color. It's not going to happen tonight. Sideways for some reason. So let's see, this is our parabola, and this is 1. So the tangent line at 1, let's draw that in green. So here is the tangent line. And if we extend it to there, then the change in y is just the difference between the y values, where delta x is 1, so we go from 1 to here, which would be 0, and delta x and dx are taken to be the same thing. All right? But then dy is the distance from this y value, which of course is 1, and this y value, which is where the line hits here. And this difference is going to be dy, and that's 1 half. That's what we calculated. All right? So what we end up doing is that we end up approximating the distance from here to here, which is delta y, by dy, which we can calculate. Now this doesn't make a whole lot of sense right now because you're looking at the whole picture. And really, I've got to tell you that the real world problems that you're going to face, there is no graph. The graph is unknown. All you'll know is here is a point, a data point that you actually have. And here is what you can compute. You can compute that the tangent line looks like this. Right? What you don't know is what the curve looks like. It will be unknown. And there's good reason for that, because you just don't know what it is. You don't have a formula for it. But you have some information about which way the wind is blowing, which way it's growing, which allows you to construct the linearization for the function, even though the function is unknown. And so if you take a baby step in either direction and follow this green line, it's just like following the curve. Now here, of course, we didn't take much of a baby step. Delta x is a huge step, a giant step, compared to how close we have to be here to have the line and the curve approximate one another. But this was an exercise that just had us calculate dy, and we can see that dy is just, you just calculate it. Take the derivative, plug in the point where you're calculating the slope, and multiply by the value of dx, which is the same as delta x, and you get your dy. And the approximation that we do in practice is dy is the approximation that we use for the unknown delta y. Okay, notice what happens if we take the delta x on the other side. It's the same kind of thing. It's nothing, nothing fancy, nothing surprising. Our function is still going to look like this. Except here's our 1, and now if delta x is taken this way, then here's our delta x, which is still 1, and that's the same as dx. Our point is here. The tangent line, I'm going to draw the same way here. Tangent there. But as you can see, the tangent line is only good as long as you're close to 1, and then it deteriorates. So question of what is dy says how much difference is there between this y value right here and this y value up here, both of which are directly above 2. So the distance from here to here, this is our dy, and the distance from here to here is our delta y. Okay? So you see the difference. This is delta y. That's how much the function actually grows from this point to that point, the change in y. dy is the distance along the tangent line. And we don't generally know, we don't often know delta y in practice, but we approximate it with dy. Okay, so once again, what is dy? dy is, by definition, the derivative times dx, because dy dx is the derivative. So dy would be 1/2 x to the minus a half, we already did that, times dx, which is the same as delta x, which is 1. Then we have to calculate that derivative at x equal to 1. It's the same thing that we had before. So this is going to be 1/2 times 1. So dy is still 1/2. And delta y is the difference between, this time it's the difference between the y value here and the y value here. The y value here is the square root of 2, and the y value here, of course, is square root of 1, which is 1. So this is our delta y, and this is our dy. So we're taking square root of 2 minus 1 and saying that that's approximately 1/2, which is rather crude because, I mean, a distance of 1 is like a real huge, giant step. But this is what the problem expected, and this is the kind of picture that we wanted you to draw. Okay, that's enough for quiz 21.